Planet Semicon welcomes you to explore the field of semiconductor physics and technology, the foundation of microelectronics and VLSI design engineering.
Welcome to this video on latch-up phenomenon in CMOS logic gate structure. A latch is a bistable switch that operates as open in off state and a short in the on state. In a CMOS gate structure has built-in shunt parasitic latch. Breakdown of the undesirable latch leads to logic gate burnout, and this phenomenon is known as latch-up. In this video, we will identify CMOS structural parasitics, latch structure, breakdown, and its prevention methods. The figure shows a typical CMOS inverter gate structure. It employs N and P MOSFETs and realize various logical functions. The input signal at A drives both the MOSFETs and produce an output at Y. PMOS provides the source current and NMOS sinks it. From figure we observe the presence of a parasitic latch across the logic gate supply. When the supply voltage becomes greater than the latch breakdown, the latch switches on and creates a short circuit across the supply. In this state of operation, unless externally controlled, the gate draws short-circuit current that leads to a catastrophic failure. Semiconductor devices are made up of combination of different material layers. The proximity of layers creates parasitic elements like capacitance, inductance, and creates phenomenons like coupling and induction. Parasitics impose constraints on the device static and dynamic parameters and behavior. We will now review parasitic element present and properties that are relevant to our current topic. Two differently doped P and N materials, when brought into contact, creates a P-N junction. Free carriers from either side migrate to the opposite side, recombine and create a charge-free depletion region. The accumulated charges on either side form an internal potential barrier and stops further migration. Depletion layer sandwiched between two conductive layers forms a parasitic capacitor. The silicon bar resistivity creates parasitic resistance. A reverse biased diode acts as a parasitic capacitor and generates static electric field across the depletion region. The bonded electrons of the depletion region atoms get polarized and realigned to the external potential. This static charge creates electric field and stores static energy. A heavily doped junction creates a narrow depletion width region, creates high field intensity and experiences Zener breakdown. A lightly doped junction creates wider depletion width region. At higher reverse bias, the static field intensity dislodges electrons, accelerates, collide and impart energy to create avalanche. This carrier multiplication phenomenon is known as avalanche breakdown. Thus the reverse bias diode, that is a parasitic capacitor, enters into electrical breakdown. Conceptually, a bipolar junction transistor is made of two oppositely connected series diodes. Heavily doped emitter base junction is forward biased and emits carriers. The lightly doped, reverse biased collector base junction collects them. BJT acts as a non-ideal constant current source. The base current is magnified by beta times and create collector current. The BJT has inherent built-in internal feedback and is represented by early effect. The BJT current gain varies and depends on operating conditions like temperature, collector emitter voltage and current. As shown in the figure, collector emitter breakdown voltage varies with the emitter base operating conditions. The magnified collector base leakage results in increased collector leakage and lowers the collector emitter breakdown voltage. Open base emitter condition creates the lowest output breakdown voltage VCEO. Base emitter with shunt resistor, the collector emitter breakdown increases to VCER. Shorting or reverse biasing the base emitter further increases the output breakdown voltage to VCS and VCX respectively. Thus collector-emitter breakdown can be controlled by changing the base emitter operating conditions. As shown in the figure, source, substrate and drain regions of a MOSFET creates a parasitic BJT structure. Reverse bias drain creates depletion region, through which the drain current flows. As the drain voltage is increased, the drain carriers gets accelerated and acquire high kinetic energy, and are called hot electrons. The gate voltage deflects some of the hot electrons towards gate oxide, gets trapped, degrade gate oxide and reduce gate capacitance. Some of the hot electrons flowing will collide with drain structure and liberate electron-hole pair. Thus liberated electrons are collected back by drain and holes are collected by the substrate. The hole current creates an IR drop in the substrate resistance, forward biases parasitic BJT and starts conduction. As this process continues, FET loses gate control and the parasitic BJT starts multiplying the carriers and enters into the avalanche breakdown. A PNP 4-layer, 3-junction device acts as a solid-state switch. Different layer pins brought out of the structure creates devices like diac, SCR, put and triac. Diac biased in first quadrant operation, forward biases, first and third junction and reverse biases the second. Increased bias breaks the second junction into primary breakdown and undergoes energy dissipation. This device enters into secondary breakdown, leading to negative resistance region of operation, makes the device to lose forward voltage blocking capability. Thus the device now enters into on state, starts conduction, and exhibits low voltage drop. The negative resistance characteristic makes the PNPN device a solid-state switch. We will now review a CMOS inverter logic gate structure and identify associated parasitics that create the latch and study its breakdown characteristics. In a CMOS structure, P and N MOSFETs are mounted, one in a well and the other in the substrate. CMOS structure has built-in parasitic elements like BJT created by source, channel and drain layers. Overlapping and reverse biased, well substrate-like layers form PN junctions. Resistors are created by distributed well and substrate-like layers. Capacitors are created by overlapping and isolated layers. These parasitic influence and limit the static and dynamic performance of a CMOS logic gate. As shown in the figure, well, substrate and source layers of FET form a parasitic NPN and PNP transistors. BJTs get interconnected with common well and substrate layers and form a latch. From figure, we observe that the parasitic latch and logic gate are in parallel and connected to a common supply. Both gate and parasitic latch experience the supply variations like noise, glitches, bounce, over and undershoot, etc. In case of shunt parasitic switch breakdown, the logic gate goes into latch-up condition that may lead to catastrophic failure. We will now study the operation of a typical solid-state latch. From schematic, we observe that the BJTs are operating in open emitter base condition and results in output VCEO breakdown operation. BJTs connected in positive feedback loop forms a latch. At low supply voltage operation, latch leakage currents are low, it operates in forward blocking state and acts as an open circuit. As supply voltage is increased, when the positive feedback loop current gain reaches unity, the latch enters into primary breakdown VBRO and starts conducting. In a forward blocking state switch, the leakage current flowing for a period of time leads to energy or secondary breakdown. The device operating in secondary breakdown state loses voltage blocking capability and enters into negative resistance state and goes into on state. This phenomenon is known as latch-up condition. For normal logic functioning, parasitic switch breakdown voltage has to be far greater than the maximum operating supply voltage. From CMOS inverter structure along with the latch shown in the figure, we observe that the BJTs, emitter base junction, are shunted by distributed well and substate resistances. This configuration helps in reducing the latch input current and thereby improves the latch breakdown voltage. As shown in the schematic, the distributed well and substrate shunt resistances reduce input currents of the latch and increase its breakdown voltage. However, the latch breakdown being less than VDD, needs further increase of latch breakdown voltage capability. The schematic shows the parasitic BJT's emitter base junctions are shunted with additional resistors and are known as taps. These shunt resistances further bypass the latch input current and improve the latch breakdown voltage. As these discrete shunt resistors can be independently selected, the latch breakdown voltage can be extended beyond maximum logic gate operating voltage and prevent occurrence of the latch-up condition. The latch breakdown voltage is enhanced by adding shunt resistors across emitter base junction of the parasitic BJT. A resistor in semiconductor process is created by a diffusion layer and are called taps. A P plus diffusion layer is created in P substrate and N plus diffusion layer is created in N well. Figure shows a CMOS inverter structure, mounted with well and diffusion taps. One end of the tap is connected to supply and the other end lies on well or the substrate. The figure shows a CMOS inverter layout structure with built-in well and substrate taps that overcomes latch-up issue. We will now review the layout structure of a well and substrate tap. In device fabrication, diffusion layers are fabricated on an implant layer and these in turn are fabricated over a well or substrate layers. Diffusion layers along with others form a well or a substrate tap. A metal layer is deposited over diffusion layer, acts as a power strap. For creating low resistance power straps and for better thermal compatibility of diffusion and metal layers, metal contacts are created at regular spacing. These contacts will parallel the diffusion and metal layers, reduce power strap resistance, lowers power dissipation and temperature raise and improve thermal compatibility of diffusion metal layers. Figure shows the CMOS inverter layout with built-in well and substrate taps built into VDD and VSS power straps. Other methods employed to prevent latch-up occurrence in a CMOS gate are increased spacing between PN and MOS device, increased well and substrate doping, reduced power bus resistance by increasing metal width, incorporating guard rings around MOSFETs, increasing as many contacts as allowed by design rules, reduce supply transients of ground and supply bounce, oxide trench isolation, epitaxial layer isolation. Thanks for your time. Hope this video has been helpful in appreciating the parasitics associated with a CMOS gate structure, latch-up occurrence and its preventive methods. Hope to meet you in upcoming video. Bye for now.